All right. Sorry about that delay. I think everything's sorted now. All right. Took a minute to get everything ready today. Sorry, my desk is just an absolute war zone right now. I have wires everywhere, and I don't really understand what they go to. Okay. I think this is good. All right. All right, let's get the show on the road here. So, I put quite a bit of stuff on here today. We'll see exactly what all we can get through. Yeah. Let's get right into it. Here. So, problem one, I have 6 series here, and again, maybe this was too many, but let's go through these and see what we can find out for radius of convergence and interval of convergence. Okay, so here we have the sum from 0 to infinity of minus 1 to the k times k x to the k. Right? So when we're computing the radius of convergence, forgot my camera. Right? When we're computing radii of convergence, what we want to do is use the ratio test on this, really, and see for what values we can make the ratio test true. So we need ak plus 1 over ak. Now here, there's no fraction, so we can literally just write ak plus 1 up top and ak on the bottom. All right. Now once we do this, we just need to simplify what we can. So up top, we're going to have negative k plus 1 times x over k. All right. That's all we're going to get here. So now we take the absolute value of this and take the limit. So limit, this k goes to infinity of ak plus 1 over ak. Right. This will be the limit. This k goes to infinity. Now here, this negative will drop off with that absolute value. So really, this just turns out to be k plus 1 over k, absolute value of x. Right? That's what it's basically going to turn out that we have. Now, this absolute value of x has nothing to do with the limit, so we can pull that out. And then we're just computing the limit of k plus 1 over k as k goes to infinity, which is 1. All right? So this is absolute value of x less than 1. Right? So this means that the radius of convergence, which I'll call ROC, this is 1. The radius of convergence is 1. All right. Well, how about the interval of convergence? So right now, the radius says, right, if we look at this, this translates to the interval. Oh, sorry, let me not do that. Absolute value of x less than 1, this turns into the interval from minus 1 to 1. And this is an open interval, right, because it's a strict inequality. The question is, does this thing converge at either endpoint? Right, that's going to determine what's going on here. Well, let's check at the left endpoint. When x is negative 1, this sum from 0 to infinity, minus 1 to the k times k, times minus 1 to the k. Right, so this sum is literally just the sum from 0 to infinity of k. Now, this one kind of obviously diverges, right? Because we're going to add 0 plus 1 plus 2 plus 3 plus 4 plus 5. And where do you think that's going to end up eventually? Right, that's a sum that's going to infinity, so this diverges. And we should say a test to make this diverge by, which in this case, the divergence test does perfectly fine. Right? Or you could do the integral test even. You could do... The ratio test won't work. The ratio test will give you 1. And that's why we have to check the endpoints separately here. All right, excellent. Now let's check at the other end. X equals 1. We're looking at the sum from 0 to infinity of minus 1 to the k, k, 1 to the k. And this simplifies to just the sum from 0 to infinity of minus 1 to the k times k. So this series will give us 0, minus 1, and then plus 2, and then minus 3, and then plus 4, and minus 5. And you can... It's probably not a surprise that that series is going to keep jumping back and forth over and over, and it's never going to settle on anything. But again, we can say that this diverges by the divergence test. All right. So the interval of convergence, which I'll write as IOC here, just to save some time, is minus 1 to 1. Right. So any question on that problem there? All right. Okay, maybe I did pick quite a bit too many of these. We'll see. We'll see. All right. Let's look at this next problem here. The sum from k equals 1 to infinity of negative 1 x to the k over, negative 1 to the k, x to the k over k squared. Right. What happens here? Well, in this one, again, we're going to start by applying the ratio test as we always do. So, ak plus 1 over ak. This will be minus 1 to the k plus 1, x to the k plus 1 over k plus 1 squared times k squared over minus 1 to the k, x to the k. Right, so again, that's a to the k plus 1 divided by a to the k. Right, so let's simplify what we can here. And this time we're going to end up with negative xk squared over k plus 1 squared. Right, that's what this will simplify to. So what will we get out of the limit here when we do the ratio test? What will we get in this case? What will this limit be equal to? Sorry, my camera's like super dark. Second. All right, any luck? Hopefully the camera looks, yeah, it looks a little bit better now. So, hopefully you're finding here that this limit is absolute value of x. All right. And again, we need to force that less than 1. So, this here says that the radius of convergence is 1 again. And this inequality, right, this tells us the same interval, -1 to 1. But now the question is, well, does that converge? Or does that converge at endpoints or not? Right? So let's go ahead and try this out. Oh, my charger popped out. Back in the, wherever the plug is. Plugged? Okay. So again, just plug in these endpoints, left endpoint, right endpoint, and see what we get. So x is -1. So if we plug that into the power series, we're going to get sum from 1 to infinity, -1 to the k, -1 to the k, over 2, no, not 2 to the k squared, right? But this series here, right, this is a p series. This is a convergent p series, right? Because p is 2, which is bigger than 1. Great, so it converges at -1. Now what about at x equals 1? Well, plug it in. Right, so at x equals 1, we plug that in. We're going to get the series from 1 to infinity, -1 to the k, 1 to the k, over k squared. So we have this series. Right? Now, does this converge or does this diverge? What do you think? And how can we show one way or the other what happens? Right, well, this series has to converge. Really, because this series does. Right? So if you look at the absolute value of this, right, if we were trying to test, say, if this thing converges absolutely, this would be 1 over k squared. And since this series converges, this one must also converge. In fact, it converges absolutely. Right? So converges absolutely, really. Because earlier series, or yeah, I'll say by previous series. Right? Because this one does, this one must also. Because remember, absolute convergence implies regular convergence. So the interval of convergence here is the interval from -1 to 1. So how about this next one here? How about number 3? Right, this is the sum from 0 to infinity of x to the k over k factorial. What happens here? Well, if we do our test here, right, so let's compute this. Right, if we simplify this, we're just going to get x over k plus 1. So when we do this limit, what we're really going to wind up with here is the limit 1 over k plus 1 absolute value of x. What is this limit going to equal? It's 0, right? So what does that mean in terms of a radius of convergence? Do you think? So if this is 0, that means no matter what x value I put in here, it's going to work. So actually the radius of convergence is infinite. And anytime you have an infinite radius of convergence, the interval is minus infinity to infinity. It's quite nice. So that means no matter what x value I put into this series here, it converges, right? Regardless of what x value I put in. Just pretty cool. I can't remember if this was the example we did in the lecture videos or not, to be honest. I know we did one with the infinite radius of convergence. At least I'm pretty sure we did. All right. You know what? Looking at the time here, I think I'm just going to jump straight to number 6 here. So let's look at the series from 1 to infinity. 2x minus 1 to the k over 5 to the k square root of k. All right, this one's a little more fun looking. So let's see what we get out of it. So a to the k plus 1 over a to the k. This is going to be 2x minus 1 to the k plus 1 over 5 to the k plus 1 square root of k plus 1 times 5 to the k square root of k, not x, not square root of x, square root of k, over 2x minus 1 to the k. All right? And simplifying what we can here, we're going to get 2x minus 1 square root of k over 5 square root of k plus 1. That's what that is. So let's take our limit here. AK plus 1 over AK. Right? So this limit here, limit as k goes to infinity. Really, again, only really this part with x's in it has the absolute value. So that's square root, I don't know why I'm writing 5. Square root of k over 5, square root of k plus 1, absolute value of 2x minus 1. And when we take that limit, think about what we get. So what's happening here? Right? We're going to get this part goes to 1/5. This just comes along for the ride. And again, we want this to be less than 1. So now, remember, the situation for finding radius of convergence, we need to get it to the form x minus a less than r. Right? This is how we check for the radius of convergence. So, this isn't done yet. So we have to take our 1/5, 2x minus 1 less than 1, and we have to start manipulating this in order to get the radius of convergence. So, oops. First things first, let's move this 5 over. So it becomes absolute value of 2x minus 1 less than 5. Quite a few fake outs there. Alright. Are we done yet? Is that ready? Are we able to say yet that the radius is 5? Okay. Are we able to say that the radius of convergence here is 5? You know, I'm always really surprised that my mic filter actually filters out the siren tests here. Anyway. So, no, the answer is we're not. We need to get this x here by itself. The way we do that is factor a 2 out of this whole thing here, so we get 2 times x minus 1/2 less than 5, which gives us that absolute value of x minus 1/2 is less than 5/2. Now we're good. In fact, we can't even say here that the center is 1/2. The radius of convergence is 5/2. Right? And then our question will turn into, you know, does it converge or diverge at the endpoints? How are we doing on time here? I'll leave that part to you to check. Right, so this interval here will say, let's see, 1/2. So this will be from -2 to 3. All right, so I'll leave it to you to check the endpoints here, whether or not it converges there. I want to get on to some of these Taylor series problems. But any questions here at all? Let's just go on to problem 2 then. Problem 2 actually asks for a Maclaurin series of this polynomial. Any guesses as to what the Maclaurin series of a polynomial is? Right? It's just going to be the polynomial itself. It actually doesn't change anything at all. Because what we're trying to do with the Maclaurin series is represent our function as a polynomial. And if it already is a polynomial, then nothing else to do. So it's simply x plus 2x cubed plus x to the 5th. That's it. Right? It doesn't have to be an infinite series. It typically will be, but if it's a polynomial, then, well, it's not going to be. Right? Problem 3. I want to find a Taylor series for x to the 6th minus x to the 4th plus 2 centered at a equals -2. Right? So how do we do this? Well, we just sort of apply the same business. So here we'll have k fk of x and whatever fk of, in this case, -2 is. Right? So 0, 1, 2, 3, 4, 5, 6, 7. All right, let's see how much of this we actually end up needing. Right? So the 0th derivative, remember, it's always just the function itself. Okay. If we plug in -2, let's see, we got 2, 4, 8, 16, 32, 64 minus 2, 4, 8, 16 plus 2. So that is 50. Okay. Now we take the derivative, 6x to the 5th power minus 4x cubed. And now we're going to plug it in again. Plug in -2 again. So let's see. -2 to the 5th times 6. So that's minus 192. And then this will be, so this will be plus 32. This is -160. Right. Take the second derivative. We're going to have 30x to the 4th minus 12x squared. So plug this stuff in. 16 times 30. The first part will be 480. And then minus 20 or minus 48. So that's 432. Right? Take the third derivative. We're going to have 120x cubed minus 24x. So let's see, 248 times 120. This will be -960 plus, again, 48, actually. So this is -912. Okay. Take the fourth derivative, 360 x squared minus 24. So let's see, 360 times 4. It's going to be 1440 minus 24. This is 1416. Take the fifth derivative. This will be 720x. So this is -1440. Take the sixth derivative, and we just have 720. So obviously this is 720. Take the seventh derivative, and we get 0. So this is obviously 0. And everything past here is just all zeros. So, as a Taylor polynomial here, f of x is going to be, we have the 0 term, which is 50, plus f prime, so -160, times x minus -2, so x plus 2. this is why we're getting all these weird numbers, right? Because we're sort of recentering this polynomial, right? Then for the second one, we're going to get 432 over 2 factorial, right, times x plus 2 squared, plus negative 912 over 3 factorial, x plus 3 cubed. And then plus 1416 over 4 factorial times x plus 2 fourth, plus negative 1440 over 5 factorial, x plus 2 to the 5th. And then finally, plus 720 over 6 factorial, x plus 2 6th. Right? So now we get to sort of expand all this stuff out, or simplify this. So we're going to get 50 minus 160 x plus 2. Let's see, 432 over 2 factorial is 216. X plus 2 squared. 912 over 3 factorial minus 152. Oops, I don't know why I put a 3 here. It's supposed to be a 2. X plus 2 cubed. Let's see. 1416 divided by 24. That's plus 59. X plus 2 to the 4th. Minus, let's see, 1440 divided by 120. So minus 12. X plus 2 fifth. And then 6 factorial, if I recall correctly, is actually 720. So this is just plus x plus 2 the 6th. So this right here, this is your Taylor polynomial centered at x equals, or sorry, centered at negative 2. So when you recenter a polynomial, you can get some weird answers like this. It's entirely possible for that to happen, but still not all that bad. Right? Any questions there? All good? Great. Okay, let's, God, I got way too ambitious. Sorry, I'm going to jump to problem 6, or sorry, problem 5, and then if there's time, I'll go back to problem 4. I don't want to keep you over time here. So, problem 5. I think this one's more interesting than 4, to be honest. Let's find a Taylor series for the square root of x at centered at a equals 16. Right? So remember, square root of x is x to the 1/2 power. Right? So this will help us when we're trying to create this this series here. So here we have k 0, 1, 2, 3, 4. Right. Fk of x. Actually, let's leave a little more room there. And Fk of 16. All right. So when we do these, we're not going to simplify a whole lot. Right? It'll make this problem a lot better if we don't. Right, so here we just have square root of x. And so this is just 4 when we plug in 16. Right? Now at k equals 1, sorry, let me rewrite this. I specifically wanted to write this as x to the 1/2. Right? So when we take the derivative, we get 1/2 x to the minus 1/2. Okay? So when we plug this in, we're going to get 1/2 times, it's actually going to be 1/4. Right? 2. When we take the derivative again, we're going to get, right, so 1/2 times minus 1/2 times x to the minus 3/2. Right? Well, let's see if we can get a pattern like this. We'll look at simplified and unsimplified answers. Right, so that's 1/8. Here, so we'll plug in x equals 4, and this is going to be 1/2 times minus 1/2 times 1/4 to the third. Okay. So this is, let's see, 2, 4, 2, 4. Oh my god, I can't do this in my head here. 4 to the third. Negative 1/256. Right. Let's see, 3 here. We take this derivative again. This is now where it gets a little more interesting. Now we're going to have 1/2 times minus 1/2 times minus 3/2 times x to the minus 5/2. Right? And then we'll have 1/2 times minus 1/2 times minus 3/2. And then here we're going to get times 1/4 to the 5th. All right. Yeah, I don't know if looking at this simplified is going to be the most helpful. Okay. So let's look at one more here. 1/2 times minus 1/2 times minus 3/2 times minus 5/2 x to the minus 7/2. Get 1/2 minus 1/2 minus 3/2 minus 5/2. And this is going to be 1/4 to the 7th power. So the reason I want to keep this apart like this is we can try to find a pattern in what's going on here. So if you look at what's happening here, this first term's a little bit odd, because starting from k equals 1, these alternate positive, negative, positive, negative. So it's entirely possible we might just have to leave the first term out. Right? But if we start from here, we're kind of getting like a so here this is for k greater than or equal to 1. These coefficients here, these are sort of giving us a if we look at the number, well, first off, it's -1 to the k plus 1, right? Because we have that alternating bit. And then underneath, look at how many 2's we have. There's a 2 to the k down here, right? And then look at what else we have going on. Right? We have 1 4, 3 4s, 5 4s, 7 4s. So we actually have a times 4 to the what would this be? I guess 2k minus 1. Right? That'll give us 1, 3, 5, 7, so on. Now the interesting part is what's going on up top. Right? Because let's see, it's 1 again, and now it's 3, now it's 5. So we're going to keep multiplying odd numbers together. Let's see. This is interesting. This is part of why I think it's fun to not do these problems beforehand. Let's see. Well, if we start this at k equals 2, then the pattern is actually one times 3 times 5 times ... times, let's see, when it's 4, I guess this would be 2k minus 3. That looks right. So this series, I think, would be we would just write out the first few terms. 1/8 x plus 16. No, minus 16. And then this starts at 2, so now we can this. There's probably a better way to do that. Oh, sorry. This isn't ck. This is the pattern in the derivatives at 16. This is going to be very interesting. All right. So let me say, all right, let me just write this for now. See if I can come up with the better answer to this. Or if I can find a better formula for this series here. So I'm pretty sure there is something that's going to work out there. But off the top of my head, I can't think about it. So I'll try and look at that before we start the next session. Yeah. I don't know, it's always fun to look at trickier problems that you have to think about for a little bit. All right. Okay, so I'm going to take a short break before we start the next problem session, and then I'll look up the, or not look up, but I'll try and get a better answer to this one. See if I can come up with a better way to write this. Then this will be posted with the problem set solutions. But as for that, I've gone way over time. So, yeah. Take care. I'll see you for the next session. And if you're here for the next session, see you in a few minutes. get started. Let's looking up one thing. Nope. Okay. Where'd the camera? All right. So I put too many problems on this problem set. So I think we're gonna do the first two in problem one and then skip a few. But let's go ahead and get started here, though, so we can get through what we can, at least. All right. So, problem one. So what we want to do is find the radius of convergence and the interval of convergence for each of these series here, or at least as many of them as we can get through. So the first one here is the sum of minus 1 to the k times x to the k. Right. We want to find out, for what values of x does this thing converge, so on. Right. So one important thing to remember about radius of convergence is we're looking for statements like this. Right. If we can write it like this, if we can get our inequality in this form, then this is the radius. The most important part is that this x has to be by itself. Now it can be just absolute value of x, or it can be x minus some number, but this x has to be alone. I've been sneezing a lot today. All right. So let's go ahead and get started. Right, so the first thing we want to do is apply the ratio test to this. So I'm going to write that out. All right, no sneeze, I guess. Until I start talking, probably. All right. So there's ak plus 1 over ak. So this is one of the rare times we can actually write everything normally, because it is all one line here. So simplify this as best we can, and we're going to get negative k plus 1 times x over, well, k. Right? That's what this will simplify to after all said and done. Hopefully that's good. Right? And once we've done that, well, now we just do our limit. Right? So let's see what we have here. So we're doing the limit as k goes to infinity. This will be of k plus 1 over k, absolute value of x. So what's the value of this limit going to be? This
absolute value of x?
Yeah, exactly. The absolute value of x has nothing to do with this limit, so you can kind of factor it out. Really, it's the limit of this times that. Right? And the ratio test wants this to be less than 1. So, less than 1. Right? Cool. So given the form that this is in right here, we can say that the radius of convergence, which I'll just write ROC, this is 1. right? Because that's this number right here. And it fits this form, right? And I'm not going to call this an interval of convergence yet because we don't know about the endpoints, but this inequality right here turns into this interval. So what we need to do then is check, well, does it converge at these endpoints or not, right? So let's do that. At x equals -1, what happens? Right? Well, at x equals -1, if we plug that into the series, we're going to get k equals 0 to infinity, minus 1 to the k times k. X to the k turns into minus 1 to the k. And so we get the sum. K goes from 0 to infinity. Well, probably not a surprise now that this is just going to be the sum of k, right? Because these two, we're going to have -1 to the 2k, but -1 to an even power is always 1. So it just goes away completely. And this, well, this sort of diverges by common sense, right? If you just add 1 or 0 plus 1 plus 2 plus 3 plus 4 plus 5, like that's going to go to infinity. But you could say this diverges by the divergence test. Well, any questions about that? So, check this at the other endpoint, x equals 1. So this is sum from 0 to infinity, minus k to the, or minus 1 to the k, times k times 1 to the k. So now, this time we get an alternating sum. This one goes 0, minus 1, plus 2, minus 3, plus 4, minus 5. So this is just going to bounce back and forth, I think, between 1 and -1, what this ultimately does. Right? That's right. But at any rate, this continually bounces back and forth by whole numbers, right? And so, or is it 0 and minus something? But anyway, this one will also diverge by the divergence test, right? Because this limit just doesn't go, it doesn't exist, right? So, cool. So both endpoints diverge. So the interval of convergence, which I'm just going to write IOC for, this is exactly that open interval we started with. Right? So again, we start by, to find interval of convergence, we start by getting this inequality from the ratio test. And remember, the ratio test is inconclusive when the ratio is equal to 1, or when the limit is 1. And the limit is equal to 1 at the endpoints of this interval, which is why we test them separately. So all those tests that we spent time learning, like this is why we did those tests, because it allows us to sort of fully describe the interval of convergence. Now, I mean, that's sort of practically why we did all those tests. They also kind of, give you some intuition about what kinds of series you should expect to converge, what kind you should expect to diverge. Well, so I mean, it has more than just a computational. All right, so let's look at the next one here. Problem 2. Right? So here we are looking at the series from 1 to infinity, -1 to the k, x to the k, or k squared. And we want to ask, what is the radius of convergence here? What is the interval of convergence here? So, same business as always. AK plus 1 over AK minus 1 to the k, x to the k, plus, oops, I forgot my plus 1. X to the k plus 1 over k plus 1 squared times, this will be k squared over minus 1 to the k, x to the k. Right. So simplify what we can here, and we're going to get negative k squared x over k plus 1 squared. And so we take our limit as always. Right? Limit of the absolute value of this stuff. So this negative gets to go away. The only thing that retains the absolute value is the part with x. So k plus 1 squared, absolute value of x. So what is this limit going to be?
Is it also the absolute value of x?
Yep. This one is still, again, absolute value of x. Because this here, you apply the same principle. This is a quadratic, or degree 2 over degree 2, so you just take the coefficients as usual. It's 1 over 1. Right? So we want this to be less than 1. And so we can see from here that the radius of convergence is 1. And this thing gives us, again, the interval from minus 1 to 1. All right, let's see if we get any different results this time, though. So, test the endpoints. Let's see, we have the sum from 1 to infinity. Yep. Negative 1 to the k. Negative 1 to the k over k squared. If you simplify that, it's the sum from 1 to infinity of 1 over k squared. Does this converge or diverge? What do you think? And why? Why does it do one or the other?
Does it converge because the limit equals 0?
So the limit equaling 0 never says that this converges.
Yeah, it converges because it's a p-series and 2 is greater than 1.
Exactly. Yeah, so this converges because it's a convergent p-series. So that's one important thing to remember about the divergence test, is it only applies if the limit is not 0, then it must diverge. If the limit is 0, it says nothing at all. Right? And again, the harmonic series sum of 1 over k, that's a divergent series. And that's sort of a good example of it. Yeah, so this is a convergent p-series. here p is 2, which is bigger than 1. So yeah, exactly. This one, that's how you attack this one. Think about this one for a second, where we plug in x equals 1. We get negative 1 to the k, 1 to the k, over k squared. K equals 1 to infinity. So this is now negative 1 to the k over k squared. So take a second to think about, whether this should converge or diverge, and if it does, converge or diverge, why it does that. And I should be right back in about 1 minute. All right. Any answers here for whether that converges or diverges? Why?
Does it converge by the alternating series test?
Yeah. So you can show that this converges by the alternating series test. There's actually another reason we already know that this converges. And this is kind of a sneaky one, but you can use this if you want. So if we take the absolute value of the terms here, we get exactly 1 over k squared. Which means if we're trying to check if this converges absolutely, we would be asking if this series up here converges. And it does. So since this converges, this actually must converge absolutely. So that's another way you could go about testing whether this converges. Right? So this is perfectly acceptable here. But I just wanted to say, hey, here's another neat little way you could do it. So at the end of the day, this tells us that our interval of convergence, it converges at both endpoints here, so -1 to 1. Right? And it is possible that you could have something that converges at one endpoint but not at the other. In fact, an example of such a series would be -1 to the k, x to the k over k. This kind of thing converges on one side but not the other. Right? And that's because on one end it's an alternating harmonic series which converges. The other side it's just a harmonic series which diverges. Right? So, kind of interesting. Right? But any questions about this problem here at all? If you're curious, specifically the interval for this one would be -1 to 1 with the bracket on the right. Okay. So, I think, let's see. So let's actually skip ahead here to number 5. Because actually, now that I think about it, I might have done. Oops, I called this problem 2. This is just part 2. I might have done number 3 in the lecture video. I can't actually remember now. But let's go ahead and hop on to number 5. Let me ask, does anyone remember that power series in number 5? Does anyone remember what this is? This is a Maclaurin series for a particular function. Thinking about that, I'll get started here on the AK plus 1 over AK. This is -1 to the k plus 1. This is going to be x to the 2k plus 3 over 2k plus 3 factorial times 2k plus 1 factorial over -1 to the k, x to the 2k plus 1. So how's that look? Hopefully that this part especially makes sense, right? Because remember, we're replacing the k with k plus 1. We're not just adding 1 to everything. So if we simplify this, we're going to have negative x squared over 2k plus 2, 2k plus 3. How does that look? Any questions there at all? Hopefully it makes sense how these factorials are canceling out. These two are the only things left over from that bottom factorial. Okay. So let's go ahead and take our limit here. Okay. So we're going to get limit as x goes to infinity of, I'm going to have 1 over 2k plus 2, 2k plus 3, right? Absolute value of x squared. Oops, I wrote 2x, 2k. Right, what is this limit going to be? What do you think? And I know that that absolute value of x is a little redundant, but it's a good idea to keep it for these types of problems.
Should it be the limit as k goes to infinity?
Yeah, it absolutely should. I didn't even notice that one.
So would it be 0?
So we get a limit of 0 here. What do you think this is going to mean about, the radius of convergence and the interval of convergence. This is to what this could imply.
The radius of convergence is infinity, and the interval of convergence is minus infinity to infinity.
Yeah, exactly. So, these numbers, they're meant to sort of say, like, for what x values does this series converge? Well, this limit is 0 regardless of what x is, so that means it converges for everything. So the radius of convergence, infinity. And if the radius is infinite, then the interval, we don't even have to do any work. It just automatically has to be minus infinity to infinity. Right? So any questions about this? By the way, this was the Maclaurin series for sine of x. So it's saying that that Maclaurin series for sine of x is valid no matter what x value we put in. Cool. So let's look at number 6, because that's an interesting one here. Right, so here we have the series k equals 1 to infinity of 2x minus 1 to the k, 5 to the k square root of k. So we want to compute the radius of convergence and interval of convergence for this thing. So ak plus 1 over ak, 2x minus 1 to the k plus 1 over 5 to the k plus 1 square root of k plus 1 times 5 to the k square root of k 2x minus 1 to the k. So simplifying this, we have 2x minus 1 square root of k 5 square root of k plus 1. And so we want to take the limit of that thing. Well, of the absolute value of that thing. So limit as k goes to infinity. And we're going to get square root of k over 5 square root of k plus 1, absolute value of 2x minus. So what's going to be the value of this limit? Different than the square root of x we had before. This part right here goes to 1. So this will be 1/5 absolute value of 2x minus 1. Less than 1. So take a minute to try and figure out what the radius of convergence is here. The radius is not 1. If you can figure it out. Do something with this. So how's that look? Any idea? Radius of convergence should be?
Would it be 5/2?
Yeah, so it'll end up being 5/2. So the way we have to do that is, remember the most important thing was, so if we have x minus a less than r, that most important thing was to get this x by itself here. So here, what we'll do is we want to factor the 2 out of that absolute value. So this becomes 2 over 5, absolute value of x minus 1/2 less than 1. And then moving that 2/5 over, you get x minus 1/2 less than 5 over 2. So here, your center is actually 1/2, your radius is 5/2. So radius of convergence, 5/2. And so this inequality here, the interval we get out of this is minus 2 to 3. So in the interest of doing some of these Taylor series examples, I'll sort of I'll leave the interval of convergence part to you to test the endpoints here. There's not much new or interesting from what we had been doing for that part. So I'll leave that to you to test the endpoints. But I really wanted to do an example of one of these radii here that are a little less obvious, that you have to do a little bit of work. Right. Any question here? Awesome. So let's look at problem 2. I wanted to toss in one of these problems, and I actually should have done it yesterday, but I forgot about it. So I put it in here because this is a really interesting one. I want to find a Maclaurin series for the polynomial x to the 5th plus 2x cubed plus x. Any idea what a Maclaurin series for this polynomial would be? Kind of a fun one. The goal of a Maclaurin series is to write or to express a function as a polynomial. Possibly infinite degree, but still a polynomial. So what do you think you're going to get if you try to take a polynomial and express it as a polynomial?
Would you get the same thing?
Yep. This right here is already the Maclaurin series. I mean, if you want, you can write it in ascending order like we normally do, but you're going to get the exact same thing. So of course you can go through and compute all the derivatives and plug in 0 and everything. But you're going to find out that you're just going to get exactly this back. Yeah, so that's a neat fact, right? Now, that's all well and good if you're finding the Maclaurin series for a polynomial. What if it's not a Maclaurin series, but a Taylor series? So I picked a function that's a little bit less fun than I had hoped, but it's okay. So here I have the polynomial x to the 6th minus x to the 4th plus 2, and this is centered at a equals -2, right? So we want to find the Taylor polynomial for this polynomial here at a equals 2. Or sorry, the Taylor series. So things actually end up getting a little more complicated this time, because remember, a Taylor polynomial centered at a equals 2 is going to end up looking like this. K equals 0 to infinity, fk of 2, or sorry, of -2, over k factorial times x plus 2 k. Right, so we're trying to sort of rewrite everything in terms of x plus 2's. So, the nice thing here is that I know exactly how many derivatives I need to take. So here, when we start trying to make a chart for this one, I know exactly how many derivatives I need. I only need to go up to 7. Or really 6, because I know the 7th derivative of this polynomial is going to be 0. Right? I got that already. Right, so now I just have to compute these various derivatives here. It's x to the 6th minus x to the 4th plus 2. Right, so let's compute all these derivatives. 6x to the 5th minus 4x cubed. 30x to the 4th minus 12x squared. 120x cubed minus 24x. 360x squared minus 24. 720x and 720. Right, so some of these aren't too bad to compute. That's 720. This is minus 440. Some of these are a little more effort. So I'm going to use Mathematica to do this. Let's see here. F is x 6th minus x to the 4th plus 2. I'm going to do d of f at x. Let's evaluate at -2. See, we're going to get 50, then minus 160. $432. minus 912. I think this one's like 1420. 1416. Remember, it was 14 something. So after 7, all of these just keep being 0 forever, because the derivative of 0 is just always 0. So, well, that means then, to compute the polynomial here, right, we just do f of x is, we take the 0th term plus the first term times x plus 2. Let me make sure that looks like 160 and not 160. And then plus, it'll be 432 over 2 factorial, x plus 2 squared. Okay. Plus negative 912 over 3 factorial, x plus 2 cubed. Plus 1416 over 4 factorial, x plus 2 to the 4th, plus negative 1440 over 5 factorial, x plus 2 to the 5th, plus 720 over 6 factorial, x plus 2 to the 6th. And these numbers actually do simplify down a bit nicer. Every single one of these is an integer. In fact, this one here is 1. But seeing as we only have a few minutes left, I think I'll kind of just leave it like this. Or in fact, let me do this. I did this in the earlier session. So it ends up simplifying down to this here. So you get some nice numbers out of it, but what this does kind of show is that, you know, if you take a polynomial and you try and center it somewhere other than 0, it's probably not going to look too good. Now, that's not to say that it can't look good. Sometimes it actually might look better that way. You might simplify some things. Yeah. So like, for example, the equation of a parabola, if you center it at its vertex, you're going to get a much simpler expression than if you didn't. Right? Anyway, so I want to do one more example here, and I jumped to problem 5 in the last session, but that one ended up being a bit trickier than I thought. So I think let's do problem 4 instead. But I do still want to try and come up with a series for problem 5. So I might, after this one, just do that and see if we can get a nice closed form for it. Sometimes it's not possible, though, to get a closed form expression. Just a heads up on that. Anyway, so let's look at problem 4. Right, so we want to find a Taylor series for cosine of x centered at pi over 2. Right? So cosine centers better at 0, but let's do it at pi over 2 and see what happens. Right? So we're going to do the usual business. I know cosine repeats after 4 derivatives, so I'm only going to do 0, 1, 2, 3. Right? Because I know it's going to repeat after that. So we'll just settle with this. We have cosine of x. Oops. Right, and then here, fk at pi over 2. We go from cosine to minus sine x to minus cosine x to sine x. Plug in pi over 2, I'm going to get 0, minus 1, 0, 1. And and again, this will keep repeating. 0, minus 1, 0, 1, 0, minus 1, 0, 1. So that means, just like when we were doing the Maclaurin series for this, it's a good idea, since we keep having these kind of intermittent zeros here, to just write out several terms of the series and see where it goes. Like the first term is 0, and then we have plus negative 1. This will be x minus pi over 2. And then plus 0, and then plus 1 over 3 factorial x minus pi over 3 cubed, plus 0, plus negative 1, 5 factorial x pi over 2, x minus pi over 2 to the 5th, so on. So if you look at what's happening here, getting rid of all the zeros here, and just writing what's actually there, we'll have, negative x minus pi over 2 plus 1 over 3 factorial x minus pi over 2. And then, let's write minus 1/5, or 1 over 5 factorial x minus pi over 2 to the 5th. And you're going to get plus 1 over 7 factorial x minus pi over 2 to the 7th, and so on. So if you follow this pattern, you're going to see that we end up with series from 0 to infinity, minus 1. Here it's going to be to the k plus 1, because we start with a negative term this time, right? And then we have x minus pi over 2. This is going to be to the 2k plus 1, right? Because the powers go 1, 3, 5, 7, 9, so on. And the factorial on the bottom matches that. So we end up with something like this. So this is cosine of x centered at pi over 2. Right? Now, there's something interesting here that maybe you can see, maybe you can't. Which is this power series right here. What does this look like more like the Maclaurin series of? Does that remind you of the Maclaurin series of another function? Maybe not exactly, but it looks
Sine?
more, it looks more like sine than like cosine. And what you can do here, this pi over 2 is kind of throwing things off. So if you try and say, all right, well, cosine, what if I plug in x plus pi over 2, right? If I plug that into this series, I get this. And this is just going to be x to the 2k plus 1, or 2k plus 1. And now, this just has one extra negative sign from being exactly the Maclaurin series for sine. So just factor out that negative. Right? And if you do that, you can see, well, this is negative sine of x. So I don't know if you remember seeing this when you learned trig functions, but this is an identity here that if you take cosine and you shift it, this one will be shifted to the left by pi over 2. Then, is that right? Yes. Shift it to the left by pi over 2, then you're going to get exactly sine. Is that right? am I saying this wrong? We plug in 0. Oh, negative sign. Never mind. We're good. I was like, that's upside down. Yeah, so if we take cosine, like imagine the graph of cosine, and if you move it to the left by pi over 2, you get exactly negative sign. Right? That's what this kind of verifies for you. So centering Taylor series at different values allows you to get some interesting results. All right. So as far as the problem session today goes, I think we'll stop on that one. Though, like I said, I do want to try and figure out this pattern for that last problem, because we're getting something interesting. So I think I'm going to stay on a little bit longer and try and work out that problem, if only for my own curiosity. So if you want to stick around and help out with it or try it out for yourself, by all means, stick around. Don't feel like you have to, though. So if you do decide to head out, have a nice day. I'll see you next time. If you do want to stick around, let's have fun with this one. So problem 5. Problem 5 is a bit of an interesting one here. I thought it would work out nicer than it did, but a little tricky. So we want to find the oh, thanks, you too. We want to find the Taylor series for this centered at 16. So I made the chart earlier, and you get some pretty interesting things here. So here we take the kth derivative, x. So here, I really want to think of this as x to the 1/2, because it's going to make the computations down here a lot better. So the first derivative will be 1/2 x to the minus 1/2. Second derivative will be 1/2 times negative 1/2 times x to the minus 3/2. Third derivative is 1/2 minus 1/2 minus 3/2 x to the minus 5/2. 4 1/2 minus 1/2 minus 3/2 minus 5/2 x to the minus 7/2. So there's a few terms there. So if we plug in 16 here, we're going to get 4. I'm not going to simplify this stuff. Right? So this is going to be 1/2 times 1/4 to the 1. Right? And there's a reason I don't want to simplify this to 1/8. Right? If we look at how the pattern's going to go, we're going to get 1/2 times minus 1/2 times 1/4 cubed. Then here we're going to have 1/2 minus 1/2 minus 3/2 1/4 to the 5th. And let's see, 1/2 minus 1/2 3/2 minus 5/2 1/4 to the 7. So we get an interesting kind of pattern going on here. So there's sort of a, let's see. So if we count up the number of 2's on the bottom in each case, it's always it's always 2 to the power k. So when we're trying to find a kth term for this, so fk of 16, there's always sort of a 2 to the k on the bottom here. So no matter what term we're at. And if we look at this, this is always sort of going to be like 4. So here we have 4 to the 1. This is 4 to the negative 1, 4 to the negative 3. Or if we flip it over, this is 1 over 4 to the minus 1, 1 over 4 to the 1, 1 over 4 to the 3. So we really want like 2k minus 1 here. And that'll take care of sort of this denominator part. Now's where it gets a little more interesting, because because this starts out positive, positive, and then negative, positive, negative. So this first term's kind of an odd one out here. Though there may be a way to fix this, to kind of embed that in the pattern. But for now, let's just say, you know, this pattern goes for k at least 1. If we do that, then this has an alternating negative 1 to the k plus 1 here. Or k minus 1, whatever your preference. It doesn't really matter. So the question is, how do you handle the numerator? So starting here, we kind of have 1, negative 1, negative 1 times negative 3. Or maybe here, this pattern, okay, this pattern will look really good starting at least 2. If we start at 2, then the numerator is 1, 1 times 3, 1 times 3 times 5. So it's products of odd numbers if we start here. So 1 times 3 times 5 times ... and let's say, what does this need to be? This needs to be 2k minus 3, I think. So if we plug in, say, k equals 4, we're going to get 8 minus 3, which is 5. So this pattern here holds for k equals 2 and larger. This kind of thing will follow this pattern. Now that's not necessarily a bad thing. We could here just say, write out the first 2 terms and then write an infinite series that starts at k equals 2. But there is a way to make this kind of thing look better. This big product here. So to bring in factorials, in other words. So the way to make this kind of thing better, so this will be sort of an aside here. If you want to multiply a bunch of odd numbers, right? And if you want to write this down in terms of factorials, right? Because this is something that's like almost like a factorial, but not quite. What we could do is say, well, let's fill in the missing numbers here. Fill in those even numbers. But then divide by them. Right, so we're not changing anything. But the beautiful thing with even numbers is we can factor a 2 out of every single one of them. So the top is now 11 factorial. The bottom is now, let's say if we factor out a 2 from each of these, we get 2 to the 5th times, well, 1 times 2 times 3 times 4 times 5. This is 11 factorial over 2 to the 5th times 5 factorial. So there's an actual pattern here in general. Let's see, if we did 1 times 3 times 5 times 9 times 11 times 13, we'd end up with 13 factorial over 2 to the 6 times 6 factorial. So if I want to do 1 times 3 times 5 up through, say, 2k plus 1, then, right, so 13, this is 2 times 6 plus 1. So this number here is the k. This is k. So it's going to be 2k plus 1 factorial over 2 to the k, k factorial. So that's going to be the general formula for multiplying odd numbers, which means if I wanted to multiply through 2k minus 3, then 2k minus 3 is 2 times k minus 2 plus 1. So this is 2k minus 3 factorial over 2 to the k minus 2, k minus 2 factorial. Is that right? Yeah, that looks good. So that means what we get down here, or sorry, that means our fk of 16, we have negative 1 to the k plus 1 over 2 to the k, 4 to the 2k minus 1, but then times this stuff, 2k minus 3 factorial over 2 to the k minus 2, k minus 2 factorial. Now there's some simplifications that happen here. So this stuff, 2 to the k and 2 to the 2k minus 2. So 2 to the k times 2 to the k minus 2. This is 2 to the 2k minus 1. Or sorry, minus 2. But something that's kind of nice is that this is 2 squared to the k minus 1. That's 4 to the k minus 1. Right? I get this right? When k is 2, we want 4 cubed. Yeah, that's good. Cool. So, if we now multiply this original denominator here all together, this is 4 to the k minus 1 times 4 to the 2k minus 1. This is 4 to the 3k minus 2. So fk of 16 is minus 1 to the k plus 1, 2k minus 3 factorial, over k minus 2 factorial, 4 to the 3k minus 2. Neat. Neat. Any more simplification that can be done here? So that means the Taylor coefficients, which is 1 over k factorial times this, What happens if we plug in k equals 1? We get negative 1 factorial top. Negative 1 factorial here as well. Alright, so that's probably as good as that's going to get. So f of x then we could say was 4. We could say it's 4 plus 1 over 8. This will be x minus 16. And then plus this series. This is going to start with k equals 2 to infinity. Minus 1 to the k plus 1. 2k minus 3 factorial. K factorial. K minus 2 factorial. 4 to the 3k minus 2. X plus 16. To the k. I get the feeling we should have something easier than this. Maybe not. Maybe not. I know there's some other tricks you can do with something called the extended binomial theorem, but I don't really want to get into that. I wonder if there's a better way to write this. Is this stuff right here almost looks like the bottom of a binomial coefficient. K choose 2 or something. Oh, plus 16. Well, at any rate, this is a nicer form than having sort of this divided by this thing here divided by k factorial. I'm still convinced there ought to be a nice way to, maybe a nicer way to write this. But I'm not sure. For now, I think I'll stick with this. I'll see if I can dig up a better way to write this. But, yeah, I don't know. These patterns and stuff are kind of fun to search for. Polynomials do really... actually, not polynomials. Factorials do quite interesting things. Yeah, if you come up with any ideas to make this look better, you know. I think I'll stop there. So, I'm not much of a combinatorist. Would that be the word for it? You study these kind of like patterns and sort of finite math pattern recognition counting problem things in combinatorics. So if that's something interesting, be a class to look at. But I'm not good at that stuff. I'll have to actually look up stuff from here. Yeah. Yeah, I think I'll stop here before I get too far into this. Well, thanks for sticking around. And with that, a great afternoon. See you on Friday.